Hello and welcome. Today, we're diving into the practical applications of geometric sequences, focusing on financial mathematics and real-world scenarios. By the end of this video, you will be able to model growth and decay using geometric sequences, calculate compound interest for various compounding periods, understand and account for inflation, and use a financial calculator's TVM solver to solve complex problems. These skills are not just for exams. They are essential for making informed financial decisions in your life. Let's get started. Our first topic is growth and decay. This is a direct application of geometric sequences to real-world situations. You'll typically see this when a quantity increases or decreases by a fixed percentage over time. Think of population growth, radioactive decay, or even the value of an investment. In these scenarios, we often start with an initial condition at time zero. This is why we introduce a zeroth term, u0. The formula we use is u_n equals u0 times r to the power of n. Here, u0 is the initial amount, r is the growth or decay multiplier, and n is the number of time periods. The multiplier, r, is key. If a quantity increases by a percentage, say p%, the new value is 100 plus p% of the original. So r is 1 plus p over 100. If it decreases, r is 1 minus p over 100. Let's look at an example. The initial population of rabbits on a farm was 50. The population increased by 7% each week. We want to find the population after 15 weeks. First, we identify our values. The initial amount, u0, is 50. The percentage increase is 7%. This means our growth multiplier, r, is 1 plus 7 over 100, which is 1.07. The number of time periods, n, is 15 weeks. Now we can plug these into our formula. U15 equals 50 times 1.07 to the power of 15. Calculating this gives us approximately 137.95. Since we can't have a fraction of a rabbit, we round to the nearest whole number. So after 15 weeks, there are 138 rabbits. Now, what if we want to know how long it will take for the population to reach 500? This time, we know the final amount, un, is 500, and we need to find n. Our equation becomes 500 equals 50 times 1.07 to the power of n. To solve for n, we first isolate the exponential term. Dividing both sides by 50 gives us 10 equals 1.07 to the power of n. To solve for n, we use logarithms. Taking the log of both sides, we get n times log of 1.07 equals log of 10. Solving for n, we find it's approximately 34.03 weeks. So, it will take approximately 34 weeks for the population to reach 500. We have now seen how to use the growth and decay formula to find a future value and to find the time it takes to reach a certain value. Let's move on to a cornerstone of finance, compound interest. Compound interest is the interest on a loan or deposit calculated based on both the initial principal and the accumulated interest from previous periods. It's often called interest on interest. This is different from simple interest, which is only calculated on the principal amount. Compound interest leads to much faster growth. The formula for compound interest is u-n equals u0 times the quantity 1 plus I, all to the power of n. Here, u0 is the initial investment in principal, I is the interest rate per compounding period, and n is the total number of compounding periods. It's crucial to understand that I and n are based on the compounding period, not necessarily the number of years. Let's work through an example. Suppose you invest $5,000 for 4 years at 7% per annum, compounded annually. We want to find the final amount. Since it's compounded annually, the period is 1 year. The interest rate per period, I, is 7%, or 0.07. The number of periods, n, is 4 years times 1 period per year, which is 4. Plugging these into the formula, we get u4 equals 5,000 times 1.07 to the power of 4. This calculates to approximately $6,553.98. So after 4 years, your investment will be worth $6,553.98. Now, let's see what happens with more frequent compounding. Suppose the same $5,000 is invested for 4 years at 3% per annum. but this time it's compounded quarterly. Quarterly means 4 times per year, so the number of periods, nen, is 4 years times 4 periods per year, which is 16. The annual rate is 3%, but we need the rate per quarter. So I is 3% divided by 4, which is 0.75%, or 0.0075. Notice how both n and I have changed to reflect the quarterly compounding. The calculation is now U16 equals 5,000 times 1.0075 to the power of 16. This gives us approximately $5,634.96. Even with a lower annual rate, the more frequent compounding can lead to significant growth. We have now learned how to calculate compound interest for both annual and more frequent compounding periods. Remember to always adjust your I and N values to match the compounding frequency. Sometimes, we know the final amount we want to achieve and need to figure out how much to invest initially. This is called finding the present value. Let's look at an example. How much does Ivana need to invest now to have $10,000 in 4 years if the interest is 8% per annum, compounded twice annually? First, let's break down the compounding. Twice annually means half yearly. The number of periods, n, is 4 years times 2 periods per year, which is 8. The interest rate per period, I, is 8% divided by 2, which is 4%, or 0.04. Now we use our compound interest formula, but this time we're solving for U0. We have 10,000 equals U0 times 1.04 to the power of 8. To find U0, we divide 10,000 by 1.04 to the power of 8. This gives us approximately $7,306.90. So Ivana needs to invest $7,306.90 today to reach her goal. We have now learned how to rearrange the compound interest formula to find the initial investment required. Now, let's talk about a concept that affects everyone. Inflation. Inflation is the general increase in the price of goods and services over time. It reduces the purchasing power of your money. In other words, a fixed amount of money will buy less in the future than it does today. This is important for financial planning. If you save $5,000 to buy something in 3 years, and inflation is 2.5% per year, the item will likely cost more than $5,000 by then. To find out how much you'll need, you must index the value for inflation. This is calculated using a formula very similar to compound interest. UN equals U0 times 1 plus the inflation rate, all to the power of n. Let's use the painting example from the notes. A painting costs $5,000 today. If inflation averages 2.5% per year, how much will it cost in 3 years? Here, U0 is $5,000. The inflation rate is 2.5% or 0.025, and n is 3 years. The index value is 5,000 times 1.025 to the power of 3, which is approximately $5,384.45. This means that in 3 years, you'll need $5,384.45 to buy the same painting that costs $5,000 today. We have now learned how to calculate the future cost of an item by indexing it for inflation. Now we can combine our knowledge of compound interest and inflation to find the real value of an investment. The real value of an investment is its final value in terms of today's purchasing power. It tells you how much the investment is truly worth after accounting for the erosion of value caused by inflation. To find the real value, we first calculate the final value of the investment using the compound interest formula. Then, we divide that final value by the inflation multiplier. Let's look at an example. Gemma invested $4,000 for 5 years at 4.8% per annum, compounded half yearly. Inflation averaged 3% per year over the period. First, let's find the final value of the investment. Half yearly means 2 times per year, so n is 5 years times 2, which is 10 periods. The interest rate per period, I, is 4.8% divided by 2, which is 2.4%, or 0.024. The final value is 4,000 times 1.024 to the power of 10, which is approximately $5,070.60. So Gemma's account will have $5,070.60. But what is that worth in today's money? To find the real value, we divide the final value by the inflation multiplier. The inflation multiplier is 1 plus 3% to the power of 5. So we divide $5,070.60 by 1.03 to the power of 5. This gives us approximately $4,373.94. This means that while Gemma's account grew to over $5,000, the real purchasing power of that money is only equivalent to about $4,374 in today's dollars. Inflation significantly reduced the real return on her investment. We have now learned how to calculate the real value of an investment by accounting for inflation. Just as assets can grow in value, they can also lose value over time. This is called depreciation. Depreciation is the loss in value of an item over time due to wear and tear, obsolescence, or other factors. Think of a car, a computer, or machinery. Mathematically, depreciation is very similar to compound interest, but instead of adding a percentage, we subtract it. The formula is UN equals U naught times the quantity 1 minus D, all to the power of N. Here, U naught is the initial value, D is the rate of depreciation per period, and N is the number of periods. The common ratio for this geometric sequence is 1 minus D. Let's look at an example. An industrial dishwasher was purchased for £2,400 and depreciated by 15% each year. We want to find its value after 6 years. Here, U naught is 2,400. The depreciation rate D is 15% or 0.15, and N is 6 years. Plugging these into the formula, we get U6 equals 2,400 times 1 minus 0.15, all to the power of 6. This simplifies to 2,400 times 0.85 to the power of 6, which is approximately 905 pounds and 16 pence. So after 6 years, the dishwasher is worth only 905 pounds and 16 pence. We have now learned how to calculate the depreciated value of an asset using a geometric sequence. For more complex financial models, especially when you need to find a variable other than the final amount, we can use technology. Most graphics calculators have a built-in finance program called a TVM solver. TVM stands for Time Value of Money. The TVM solver allows you to input several financial variables and solve for the one you don't know. The variables are N, the total number of compounding periods; I%, the annual interest rate; PV, the present value or initial investment; PMT, any regular payments, which we'll set to 0 for now; FV, the future value or final amount; P/Y, the number of payments per year; and CY, the number of compounding periods per year. There are a few important conventions to remember when using a TVM solver. First, the initial investment, PV, is entered as a negative value. This represents money leaving your pocket. The future value, FV, is positive, as it's money you receive back. Second, N is the total number of periods, not years. And third, I% is always the annual interest rate. Let's revisit an example. Sally invests $15,000 at 4.25% per annum, compounded monthly for 5 years. How much is her investment worth? We want to find FV. N is 5 years times 12 months, which is 60. I% is 4.25. PV is negative 15,000. PMT is 0. PY and CY are both 12 for monthly compounding. Inputting these into the solver gives us an FV of approximately $18,544.53. The TVM solver is a powerful tool that can save you time and reduce errors. We have now learned how to use a TVM solver to find the future value of an investment. The TVM solver is incredibly versatile. Let's see how we can use it to find other variables. First, let's find the present value. Helena wants to have $5,000 in 3 years, with an interest rate of 5.2% per annum, compounded quarterly. How much should she deposit now? We are looking for PV. N is 3 years times 4 quarters, which is 12. I% is 5.2. FV is 5,000. PY and CY are 4. Solving for PV gives us approximately negative $4,282.10. The negative sign just confirms it's an initial investment. So Helena needs to deposit $4,282.10. Next, let's find the time it takes for an investment to grow. Magnus invests $4,000 at 6.45% per annum, compounded half yearly. How long will it take for his investment to reach $10,000? We are looking for N. I% is 6.45. PV is negative 4,000. FV is 10,000. PY and CY are 2. Solving for N gives us approximately 28.87. This is the number of half years. To find the number of years, we divide by 2, which is about 14.43 years. Finally, let's find the interest rate. Yaman deposits $5,000. 2.5 years later, the balance is $6,000. The interest is compounded monthly. What was the annual interest rate? We are looking for I%. N is 2.5 years times 12 months, which is 30. PV is negative 5,000. FV is 6,000. PY and CY are 12. Solving for I% gives us approximately 7.32. So the annual interest rate was 7.32%. We have now seen how to use the TVM solver to find the present value, the time, and the interest rate of an investment. This tool is incredibly powerful for solving a wide range of financial problems. Let's quickly recap what we've covered today. We started with growth and decay, using the formula U-N equals U0 times R to the power of N. We then moved to compound interest, using UN equals U0 times 1 plus I to the power of N, and learned how to adjust for different compounding periods. We also discussed inflation and how to calculate the real value of an investment, and we looked at depreciation. Finally, we explored the TVM solver, a powerful tool for solving complex financial problems. You are now equipped to model various financial scenarios using geometric sequences. To solidify your understanding, here are 5 practice questions. Question 1. A car bought for $30,000 depreciates at 18% per year. What is its value after 4 years? Question 2. How much must be invested now at 6% per annum compounded monthly to have $12,000 in 5 years? Question 3. An investment of $8,000 grows to $10,500 in 3 years, compounded annually. What was the annual interest rate? Question 4. A population of 200 increases by 5% each year. How long will it take to reach 500? In question 5, an investment of $10,000 earns 4% per annum, compounded quarterly. If inflation is 2.5% per year, what is the real value of the investment after 10 years? Pause the video here and try to solve them. The answers will appear in a moment. Here are the answers. Check your work and make sure you understand how to arrive at each solution. Thank you for watching.